Okay, so we're surrounded by aluminum pretty much every single day, right? But have you ever really stopped to think about what gives this metal its strength? Well, it turns out the answer is this incredible story that starts in molten liquid and ends in a hidden microscopic world. So I want you to picture this. You run a smelter. You've just made a whole batch of these huge, shiny, perfect-looking aluminum ingots. But when you go to test them, they just crack. They fail. They're brittle, weak, totally useless. So what's the deal? How can something that looks so solid be so fragile? And this isn't just some textbook problem. For a real industrial operation, a bad batch like this can shut everything down. We're talking millions of dollars lost. So solving this mystery, it's not just for kicks, it's about staying in business. So there you have it. We've got a genuine industrial mystery on our hands. A whole batch of what should be perfectly good aluminum has gone bad, and we have got to figure out why. So let's put on our detective hats and start digging. Okay, first clue. You run a chemical analysis, and guess what? The aluminum is pure. The recipe is right. That tells you something huge. The problem isn't the what, it's the how. The flaw is hiding somewhere in the process itself, specifically in that journey from a fiery liquid to a solid block. To follow that clue, we have to zoom in. I mean, way in, to a level that you just can't see with your own eyes. We need to take a look at the metal's hidden architecture. And that brings us to this absolutely critical idea, the microstructure. The best way to think about it is like the steel frame of a skyscraper. You can't see the beams inside the walls, but they're the only thing that determines whether that building stands up or falls over. It's the exact same thing with metal. This invisible network of tiny crystals or grains dictates pretty much everything. And wow, this picture says it all. Look at this. On the left, that's the inside of our brittle, failed ingot. See how the crystals are all big and coarse, kind of branch-like? Now look at the right. This is a strong, solid piece of aluminum. The whole structure is fine, it's dense, it's compact. It's the same exact material, but two completely different internal worlds. This right here is where we solve our mystery. So the big question is, how on earth do you get two totally different results like that? To figure that out, we have to rewind the tape to the exact moment this architecture was built, during solidification, when that molten aluminum cooled down and became solid. This graph is called a cooling curve, and it's basically a secret diary of the metal as it becomes solid. It's not just a smooth, straight drop in temperature. See that flat spot right around 571 degrees Celsius? That's not an error. That's the moment the liquid aluminum is so busy snapping its atoms into solid crystals that it actually gives off heat, which pauses the cooling for a second. It's like the metal's birth certificate, and it's telling us a story. Now, this whole transformation really happens in two key steps. The first is called nucleation. Just think of it as the very first seed of a crystal forming. A few atoms just snap together into a pattern. Then comes growth, where more and more atoms from the liquid attach themselves to that seed, making the pattern bigger and bigger, kind of like a snowflake growing. And it's these growing crystals, these grains, that end up creating that entire internal architecture we were just looking at under the microscope. The final size and shape of these grains are what make the metal either strong or weak. So this is where it all comes together. If nucleation and growth create the microstructure, then what controls them? Well, the answer, and the thing that solves our whole mystery, is just one variable: the speed of the cooling process. And here it is, the smoking gun, right here in the data. When they cooled the aluminum really slowly, at just 0.17 degrees a second, the grains ended up being huge, and that gave them a brittle ingot. But when they cooled it more than 30 times faster, the grains were way smaller and much more compact, and that's our strong ingot. Case closed. And you don't just have to take my word for it. The research confirms it directly. This quote from the paper says it all. Higher cooling rates produce smaller, more rounded, and ultimately stronger grain structures. So why does that even happen? Well, think of it this way. Fast cooling creates a kind of panic in the molten metal. A gazillion tiny crystal seeds form all at once, but none of them have any time to grow before they run into their neighbors. This creates a fine, interlocking, very strong structure. Slow cooling is the opposite. It's lazy. Only a few seeds form, and they have all the time in the world to grow huge and sprawling, which results in a coarse, weak structure. Okay, so we've solved the mystery. Now what? How do we use that knowledge? Well, this is where the science becomes engineering. Once you know the why, you can control the outcome and intentionally build strength into the metal from the very start.
So how do they do it? Well, first, as we've seen, they precisely manage that cooling rate. Second, they can add things called grain refiners, tiny particles of stuff like titanium that act like pre-made seeds for crystals to form on. This forces a fine-grained structure. And third, they work really hard to remove impurities because as crystals grow, they can push junk into the boundaries between the grains, creating these built-in weak spots.
So really, the main thing to take away from all this is that metallurgy is like microscopic architecture. If you can control the conditions when the crystals are born, you can dictate the final properties of the metal. You're not just making a lump of aluminum, you're literally building its strength from the atom up.
Which brings us all the way back to our first question, but now we have a much, much deeper way of looking at it. What really makes that piece of metal strong? Is it just the atoms it's made of? No. It's the story of its creation. Its strength comes from its journey, from the chaos of a liquid to the order of a solid. A story that's written in an invisible architecture of crystals, where speed, timing, and purity decide everything.